Okay, so some of the evidence supporting continental drift was presented earlier in the chapter. However, new supporting data as well as new interpretations helped with the new model for the theory of plate tectonics. In the following slides, we'll go through 3 ways in which more evidence was collected that supported this theory. So the first way was ocean drilling. Some of the most convincing evidence for seafloor spreading came from the deep sea drilling project, which operated from 1966 to 1983. One of the earlier goals of this project was to collect enough samples in the ocean floor to establish the ocean floor's age. So the Glomar Challenger was the ship built that was collecting these samples that were thousands of meters in depth. They drilled into the ocean floor, collecting the overlying sediments as well as the underlying basaltic rocks. So the scientists used fossil remains in the sediment that was resting on the basaltic crust at each site to examine the age of the seafloor rather than using radiometric dating, which can sometimes be tricky in oceanic rocks because of the alteration by by the seawater. So they used the fossil remains to find the specific age of that crust, of that sediment that was lying on top of it. So when researchers recorded the age of the sediment from each drill site and its distance from the ridge crest, they found that the sediments increased in age with increasing distance from the ridge, which meant that the youngest crust would be located nearest to the ridge and that the oldest adjacent to the continent, so the furthest away from that ridge. They did not find old organisms in areas nearest to the ridge, for example, which meant in those areas that were newer. There had been lesser time for deposition of sediments where the fossil remains would also decay onto and be buried by. So, as you're seeing in the image here, these are the different organisms that were found, or different sediment packets that were found. And for example, organisms that were old, like the one found in this sediment packet and the white one, were not found in this drill core that was closest to the ridge, right? So the newer the crust, the less amount of sediment thickness and less amount of older fossil remains that there were, which is pretty cool. So the distribution, again, and the thickness of these sediments provided additional verification of seafloor spreading. Cores from the Glomar Challenger, which was again that ship that collected the samples, revealed that there were nearly no sediments that accumulated on cores nearest to the mid-ocean ridge, and that sediments increased in thickness as they were further apart from the ridge. So they increased in thickness as the distance from the ridge also increased. So this deep sea drilling project also supported the ideas that ocean basins are relatively young because no seafloor age older than 180 million years was found. By contrast, most continental crust exceeds several hundred million years of age, with some samples being even 4 billion years old, which are pretty much the oldest rocks that we have on the planet. But that also contributed to the fact that oceanic lithosphere is very young. The deep sea drilling project ended in 1983, but since then the International Ocean Discovery Program, or IODP, uses multiple vessels for exploration of the seafloor. So a second line of evidence for the theory of plate tectonics is paleomagnetism. So this might take a little bit of time for you to comprehend, so if you need to pause the video and rewind as I go through it, I encourage you to do so. So Earth's magnetic field has a north magnetic pole and a south magnetic pole. Today, these magnetic poles roughly align with the geographic poles that are located where Earth's rotational axis intersects the surface. Not quite perfectly, but close to it. So if you see the image over here, the magnetic north lies about there, the geographic north lies about there. And that's why when you have a compass and you're hiking around or whatever you may be doing, you have to accommodate a certain amount of degrees for your compass not to point to the magnetic pole, or rather to point to it, but show you where the geographic north is. So if you're in Idaho, that amount of declination is what it's called, is going to differ than if you are in New York or something like that. Okay. All right, so the Earth's magnetic field is pretty similar to that produced by a single bar magnet, as you can see again in that same image. The Earth's magnetic field is less obvious to us as a force than the pull of gravity, for example, because we cannot feel it. However, the movement of a compass needle confirms that the magnetic field's presence is actually in our planet. And in addition, some naturally occurring minerals, like magnetite, are magnetic and are influenced by Earth's magnetic field. Again, magnetite is one of the most obvious ones, but there are other minerals like hematite that are also influenced by the Earth's magnetic field. Magnetite, however, is a mineral that is abundant in lava flows of basaltic composition. So if you guys remember, the ocean floor, as I have said in the past few slides, is mostly composed of this basaltic composition rock. So basaltic lavas erupt at the surface at temperatures greater than 1000 degrees Celsius, exceeding a threshold temperature for magnetism, known as the Curie point. So the magnetite grains in molten lavas are non-magnetic because they, again, exceed that threshold. But as the lava starts to cool, these iron-rich grains of magnetite become magnetized and align themselves in the direction of the existing magnetic lines of force. So once the minerals solidify, the magnetism they possess usually remains frozen in this position. And so they act like a compass needle because they point to the position of the magnetic field at the time of their formation. Okay, that's very key. They point to it only when they formed and they cooled. So those rocks which formed thousands or millions of years ago and contain a record of the direction of the magnetic poles at the time of their formation are said to possess paleomagnetism. Okay? So there are two ways in which paleomagnetism helped as evidence for the theory of plate tectonics. The first way was through the apparent polar wandering. So, and that's going to be the image on the left is going to help you with that. So, a study made on lava flows throughout Europe led to an interesting discovery. This study's data suggested that the position of the paleomagnetic poles had changed through time. So a plot of the magnetic North Pole location, as measured from Europe, seemed to indicate that during the past 500 million years, the pole had gradually wandered from a location near Hawaii northeastward to its present location over the Arctic Ocean, as you're seeing there in the image. This suggested that either the magnetic north had migrated or that the poles had remained in place and the continents drifted beneath them. In other words, Europe had drifted relative to the magnetic North Pole. The image on the left of the screen again shows this apparent path of polar wandering seen from Europe or from North America as well on the top image. So although the magnetic poles are known to move in a somewhat erratic path, now we know that, studies of paleomagnetism show that the positions of the magnetic poles averaged over thousands of years correspond closely to the positions of the geographic poles, meaning the wandering probably wasn't as great as the study potentially suggested. So therefore, a more acceptable explanation for this path is the apparent movement of the continents in relation to the magnetic north. Further evidence came after a polar wandering path was constructed for North America, and again that's going to be the red track as you're seeing right here. So let's see, here you see that for the first 300 million years, the path of North America and Europe were found to be similar in direction, but separated by about 5,000 kilometers or so. Then, about 180 million years, they began to converge in the present North Pole, which means that North America and Europe were joined until the Mesozoic, when the Atlantic began to open. And that is what we covered in a couple slides ago with the different plate motions that we found after Pangaea rifting. So when the two continents are moved back to the pre-drift positions, as you're seeing in the lower left image, these paths of apparent polar wandering actually coincide, meaning that once they were united and they moved relative to the poles as part of the same subcontinent, that subcontinent being Laurasia.